And it's more than 11, so we will start whenever you want.
Okay. Yeah, hello. Okay. Yeah, hello everyone. I would very much like to welcome you to my today's presentation about the accurate prediction of solid solution strengthening using the coherent potential approximation. So, in ancient times, people basically discovered that by allowing tin into kappa, one can greatly improve its strength. So, but actually, what do we mean by strength? So we mean essentially the stress at the onset of plasticity, but that's not actually the only important parameter here. It's also important.
Recording in progress.
It's also important to know how much more stress we can apply before the material fractures catastrophically. And a good measure for that is actually the toughness here. And over the time, a lot of different mechanisms and ways were discovered on how to improve actually the strength of a material. But somehow there is always this trade-off that if one makes a material strong, it gets more brittle. But basically this substitutional alloying somehow seems to be an exception, like what was done already in the Bronze Age, that it also creates very tough materials, meaning they're not really brittle and they're also strong. So what is basically happening? So if you put solutes into your alloy, it will locally distort the lattice, it will contract in some places it will expand. And these distortions of the lattice are interacting with our extended defects, our dislocations, which are responsible for the plastic deformation. So you basically create local energy configurations for the dislocation that are favorable or unfavorable, which in fact then will lead to some macroscopic strengthening effect by making it harder for the dislocation to move through the crystal. Of course, it's impossible to do explicit calculation of that with DFT or like with any other ab initio methods. It's just out of the reach. Okay. So what we are doing now is to basically use an experimentally validated model for the strength, which only takes into account bulk material properties of our alloy. So basically we just need linear elastic properties, and we need some kind of dependency of the equilibrium volume of our alloy with respect to the changes of the concentration of its components. And this is somehow a measure for the volume misfit of the solute in the matrix. Of course, we can measure it, but we want to calculate it. So in order now to be able to predict this strengthening, so basically the stress at the onset of plasticity, we need to accurately predict the equilibrium volume and the linear elastic properties. But we have disordered alloys, we have multiple components, we are interested actually in ranges where paramagnetism is very important, so conventional supercell methods would be way too demanding for doing that. So what we are using now is we are using a Green's function DFT method, where we use CPA, like the coherent potential approximation, to model the disorder. We use the disordered local moment model for basically doing CPA on moments to model the paramagnetic state. We apply some semi-empirical corrections to the exchange correlation function, and we also include finite temperature effects, phononic, magnetic, and electronic effects. All of that will give us these two quantities that we feed into the strengthening model, which finally gives our target quantity. And this whole thing with a Green's function method is quite efficient. But now we then embed this whole workflow into a machine learning framework, because we want to optimize actually the concentrations so that we want to optimize the strength with respect to the concentrations of its components. So first of all, let me explain what do we do actually with the semi-empirical correction to LDA. So we use a scheme that was actually proposed by Van der Walle and Seda. So what we do is we add to the total energy a concentration-weighted pressure that is element-specific and is calculated once and for all for the ground state of each element. So you effectively have to calculate the pressure at the experimental volume. And the reason for that is the following. So basically, if you use LDA for most metals, you get, of course, under-predicted lattice constants. But if you use experimental values, the linear elastic properties are actually quite accurate. And here you see basically some comparison. So our LDA plus correction scheme as compared to using some GGA PBE. Well, we are kind of nearer, so it really corrects this problem throughout the 3D metals and also some refractory metal alloys here. And it really improves actually the prediction of the bulk modulus and also of the other linear elastic properties. So what do I actually mean? Just very short with the temperature effect and of the magnetic moment. So what you really see with these itinerant systems is that if you, at elevated temperature, you basically get an enhancement of the magnetic moment. And this can be incorporated into DFT by some phenomenological model that was proposed by Levente-Witos, I think, and for André Ruban. And it's called actually, called the phenomenological model for longitudinal spin fluctuation. And it really helps with the equilibrium volume and also with these derivatives. Yeah, so now let's go to the results. So what we did is we calculated now with our workflow this strength. So this is then the intrinsic property. It's called the critical resolved shear stress. So basically the shear stress that is needed for moving a dislocation. And we compared it with trustable experimental results. And we also compared it by using experimental results for the model. And we really found that we actually can predict for this nickel cobalt chromium alloy the strength throughout actually a quite big temperature range. Then we said, okay, let's try to find the optimal composition, and for that we use Bayesian optimization. So that's basically just a way of how to optimize a function where we don't know the derivatives in a minimum number of steps. And so it's basically a trade-off between exploration of spaces with high uncertainty and exploitation of spaces where we know that our fit is already kind of good. So, and this is basically how it's optimizing. Okay, it's not that interesting for a 3-component alloy. I mean, one can argue one just makes a grid. But this is really important for, like, if I don't know if I want to do it with 9 components or even more, or if I want to put some constraints on it. Yeah. So to conclude, we made an efficient ab initio-based method for predicting the solid solution strengthening in now multi-component alloys. I called it here now high entropy alloys. It's quite efficient. It takes not really a lot of core hours, so you can even run it actually on your workstation. It helps finding non-equimolar alloys with favorable mechanical properties, and it's part of the Adaman software toolkit, which is effectively some kind of toolkit that helps you modeling dislocations and mechanical properties. So, and finally, I also want to advertise that we are actually developing Green's function codes, and I want then really to also thank my funding agencies, which basically keep me employed. Okay, thanks a lot, and yeah.
Okay, thank you very much. We have plenty of time for questions, so that's perfect. If someone has question, of course. Yeah.
For magnetic properties, people typically use LDA at experimental lattice parameters because of the preservation of some rules that are crucial for magnetic features. Now you modify LDA. How does this keep those some rules?
Right. So, yeah. The point is, as you said, you actually want, or you almost need to use LDA to correctly reproduce the magnetic state. But somehow it's an effect that is only taken into account like a posteriori. That means you basically just push your result to a place where it gives where it then really predicts correct lattice constants. So that's exactly the point of it, you know. So you just add a pressure, and you really know, you can even like argue like where these things are coming from. Like it's really coming from some non-local interactions in the core. So it's not considered self-consistently, and that really helps in this respect. Yeah.
How flexible is your schema? Would it be difficult to interchange the EMTO by, for example, a spinner? Is that the black box which over there is?
Yeah, I mean, so effectively it's made like this so that you can actually exchange your driver. So, I mean, the only thing, so since we're actually calculating LOS, I'm, for example, also calculating screening effects automatically by then linking to some locally self-consistent Green's function method. But generally, you can use any kind of method you want there. It's really a general way, basically. I mean, one just would need to write like kind of an AIDA interface for SPR KKR, and ensures really that the input and that the result is really stable and, how do you call it, robust.
Yeah, well, so I have in mind with it's for this high entropy errors. When we showed it, I think I had it in my talk. It's really important to include the correlations beyond the LTA or the process. So we did the BMFP, and it would be a great thing to combine it in, and try to run it.
And effectively, it's really a black box. So, yeah. Yeah. No, I mean, now it's really like this. So you can just kind of exchange I think one can, since you have this ASE, I think one can even use it as it is for AIDA, as far as I can remember.
Okay.
Yeah.
Okay, anyone else? For last question? No? Perfect. So thank you very much.
Yeah.
So fine, we're right on time.
Talking about application of Tensor Networks for quantum transport problems. And as you see in this image, it applies for a broad range of topics, not only for simply understanding quantum transport in the sense of transport through some small region, but also it can be applied in other cases. For example, and all of this kind of models, there is the same formulation. It can be applied either to molecular electronics, to some quantum thermal machines, as displayed lower, or to study Kondo effect, or even more applicable comparing to the topics of our school today, as an iterative, as an option to solve an impurity model in an iteration of the MFT method. And as I said, all of those methods carry the same kind of general overview, which means that it can be described by a similar kind of Hamiltonian. All of them has a small working element, which can be an impurity, for example, a single impurity Anderson model. It can be small molecules, and this kind of small limited finite system is coupled to potentials or the temperature, and by this difference the flow is happening. But of course there can be more of them, including, for example, at the first stage, another bosonic lead for photonic protons. As I said, the Hamiltonian will consist then of 3 parts, each for separate regions for a system, for a reservoir, and also for a coupling between them. And as we already know, the non-interactive systems can be easily tackled with known methods, for example, a Green's function formalism, or one can employ also correlation matrix methods, because then the system will be Gaussian, so it's sufficient to describe it. But for the more complicated ones, one would like to have other methods to solve the problem. And as you learn in the topic of Jan, it's not as easy to do, and one can either have a nice approximation which has the properties as we expect, or implement the system in a numerical way and treat it exactly. But in order to treat it numerically, we have to have discretized formulation of the problem. Instead of treating the whole continuous leads, we treat them as a finite number of particles which are coupled to our middle system. But as you probably expect, finite number of particles do not, even if there is a bias between them, do not allow us to study long-time dynamics, because after some time they will just spool through, everything equilibrates, and we have just ground state. So we would like to, in my topic, I would like to study a steady state which develops in a long-time dynamics. Yes, so I'll come back to this later. So I will discretize my problem by showing that leads are represented by a finite number of particles, and later I will display you how does it behave if I assume that each of these elements of these states are coupled to an external buff, which is treated effectively in a linear equation. And because we also want to go beyond the non-interactive models, I will employ the numerical method, which is called the Tensor Networks method, which bases on a factorization of our complex state and into a product of individual tensor. I showed simply here how does it happen if we have, for example, some wave function phi. It can be efficiently expressed in any basis whatsoever, just by making projection of a certain basis vectors. And by doing this, each kind of coefficient will correspond to this C element. This C element has multiple indices, and now I want to associate it, I want you to associate it with a multidimensional tensor. Now, if you treat it with any kind of decomposition method, let's say the singular value decomposition, you can decompose it into smaller parts efficiently into a chain as here, when each of those tensors will carry only the information about this physical index. And this is what I will call a separation of variables. The separation, in fact, the cost of separation depends strongly on entanglement between all of those parts. And this will be something which could be effectively measured by a single number, which is entanglement entropy. It's very nice because it's sure concave, so if the distribution of those C parameters will be more uniform, it means that also the entanglement entropy will be greater. It saturates if the distribution is equal. And of course, if it decays very sharply, I can truncate those of the smaller amplitudes, and I can express my state effectively. So now we go to the Dopant system, which I was talking about. As I told you, I expressed my leads effectively by a finite number of modes, distributed however I prefer. The discretization in principle is arbitrary as soon as I will converge to a thermodynamic limit as the number of modes increase, so that effectively the lead will become continuous. Yes, so in order to tackle this steady state, we extend our finite system by external relaxation, which will be carried out by Lindblad term, as displayed here. injection and depletion of particles for a certain mode K. And of course there are different models of such. If we assume that the Markovian relaxation happens, which means that the reservoirs relax very fast to its equilibrium, then then the whole simulation would be very simple because it becomes local in time, and it would be actually looking at like this. But if we would like to account for the broadening of modes due to coupling to external reservoirs, we have to also include the time domain problem, and the whole problem, the whole equation becomes effectively time non-local. So I will have to update what kind of distribution I will have to have each time. In my work, we studied how does the current behave in such kind of a setup when we have the relaxation either Markovian and non-Markovian, but which is treated as a parameter. So this kind of relaxation term will be weighted by a factor gamma, as displayed here. And by looking on a more non-local measure, which is a current, I'm trying to narrow the region when the flow of the current will be the most natural, the physical one in my system. Of course, for infinite numbers of reservoirs. And what we have observed here, that the whole behavior of the current is very similar to the one which is to the speed of chemical reaction in simple chemistry, which you will learn probably during your studies. The whole picture is very easily interpretable, and for the region of very weak relaxation, which means very weak gamma parameter, we see that the flow of the current is effectively governed by the strength of coupling to external reservoirs. The observation is that the current flows increases proportionally to gamma. On the other hand, when we increase the gamma parameter too much, we suppress the correlation developed in the system because we are constantly measuring it by this Midland term, by giving these occupations. By suppressing of correlation coherences, we also suppress the current flowing. The whole behavior will be like 1 over gamma for this region. In some middle region, we have the flow of the current through the impurity, which will be the most natural for our system. And this will be displayed here in between those slopes. The range of it can be dependent on the number of sites, naturally correlated with the number of particles which are accessible in this list. Sorry, I exceed my time. We also commented on the differences which and the different features which happen for with relaxation, but I won't be saying about this more. So as I said, by analyzing of this curve of current, we can find the most optimal relaxation for our system. Depending on the relaxation dynamics, of course, it can differ, as displayed here. But again, if we restrict to Markovian relaxation, the whole model is very simple. It's easy to implement with tensor networks, and it leads to a proper thermodynamic limit. Now I want to tackle more complicated systems, so I will employ it with the tensor networks. I can easily do it by writing my density matrix as a vectorization. So I will just reshape it into a vector form using this inspired Choi-Jankowski isomorphism, and write it as my tensor networks, as I showed you in the first slide. Now, if I choose the proper basis, I can also limit the entanglement in my chain. As I told you, the entanglement quantifies how big is the bond dimension D. So by ordering it according to scattering structure, I can easily limit the cost of the description of my state. And again, this kind of features which we developed and described using Green's function formalism for non-interacting methods and non-interacting models also called for the interacting ones, which is good because we can extrapolate it to these more complicated models as well. This is just to show you how are the models we studied and how does the convergence looks like in terms of one dimension, let's say, or the truncation threshold as in here, or in number of modes included in reservoirs as displayed here. In conclusion, I would like to remember that this kind of tensor networks approach we're given is a very nice thing to describe our system, provided that the entanglement is limited. Very nice thing comes with the fact that instead of the exponential scaling of our number of elements we have to include, we have the linear scaling in terms of particles, number of particles. Because we also can change how many of those singular vectors we want to include, this method is also quite nicely scalable because I just set the threshold and it's easily adjustable. Also, by knowing what will be this behavior of the current and by understanding what is happening, I can identify the relaxation strength and point to a steady state, to the real physical steady state of my system. And the last thing is that tensor networks not only give us an opportunity to solve the problem, which is many-body and not as easy to tackle the Green's functions, but also we can change the geometry of our representation in order to lower the cost of representation. Okay. Okay. So thank you. And we have
Okay, thank you very much. So maybe we have 1 minute for questions. Okay, so I have one. Something maybe that I misunderstood. So you used the single value decomposition to define your tensor network?
yeah, I mean, you can make a decomposition like easily using singular value decomposition. We're just not sure it's the question about.
It just, I don't understand how you use the Schmidt decomposition of your...
I use it in order to separate my variables.
Okay.
So as at first I've shown, the C has many indices, and each of these indices will be like a separate variable. And now I want to separate them into a product of tensor. Each one of them will be describing another variable.
Okay, so...
If I
yeah.
just put it as because usually SVD is seen for rectangular matrices.
Mm.
You can see that this multi-dimensional tensor also can be shaped in a rectangular matrix. And if you just keep a single variable index on one side and all the others on the other side, then you can effectively decouple the problem into a side which corresponds to this very index and the rest. And if you do it one by one, you decompose the whole thing in a product of tensors.
Okay, I see. And do you think you can use different embedding techniques in order to decompose your system?
Do you mean the geometry of the
No, about your wave function, such as exact diagonalization, I don't know, a different embedding method.
I'm not familiar with the name embedding.
Yeah, like your Smith decomposition, but in different way.
I mean, of course, you can make different decomposition depending on the geometry of, because what I'm thinking about the geometry of the tensor network means how is it connected? It's a single line, or if I have shown on the first second slide, it was like a lattice. But of course, it can be anything. Like it could be a tree tensor network, which just have a lot of different branches.
Yeah.
And if you know that, for example, you have single impurity under some model, and let's say it's the coupling between is zero, then you know that those channels are decoupled. So it's easier for you just to develop a network which has two branches and connects somewhere in between, let's say. And if there is an interaction, of course, they will be slightly coupled, but it will be like less. I mean,
Mm. Yeah.
Because then it will spread, there will be like a lot of correlation which you would have through,
Mm.
and because of that it will emerge.
Okay. Thank you very much. So next speaker, please. Be careful.
Thank you. I'm going to present part of my project that I did in my PhD. So the title is a bit very, not very direct to what I'm going to show, but it'll become clear. It's circulating currents and magnetic fields near single spin in a true lattice. Okay. So just to contextualize a little bit, the idea here is to look at the single spin manipulations. So in coherent manipulations and point defects in semiconductors. This is a field quite developed last years. We already have some actually industrial applications, but just to give two examples, on the left we have a silicon carbide, and on the right diamond. So in this case, diamond is called NB centers. It's basically two defects, one substitution of nitrogen close to a vacancy in a diamond. And these states are used in quantum sensing. So they provide a very good nanoscale magnetometry system, and it's similar to the silicon carbide. So the idea here is to go beyond what's usually described in this coupling. So for applications in quantum sensing and qubits and quantum computing, you need a way to manipulate prepared state and readout. And usually these couplings are done considering only the spin dipole fields. So, and the control is done via the G-tensor, basically. But the idea here is to look further into the orbital magnetic moments of these states. So I'm going to look just at the ground state properties. And it has, in the spatial structure of those, magnetic moments are quite important when we look at coupling with fast oscillating fields, like nuclear spins, that surrounded the defect. And I'll show later that these magnetic moments can also be directly measured by the fringe fields, what I call here. And this can also be measured by these NB centers that I mentioned before. And the most important ingredient in all of this manipulation is the spin-off coupling. And so I'm trying to develop a formalism that goes beyond the dipole interaction in this case, between spins. So I'll present a very kind of simplistic model, but it's a semi-analytical for the problem. So I'm looking at quantum wells with spin-off coupling and inversion asymmetric. So basically there's two important ingredients in this kind of systems. So if you look like a zinc blende crystal, we lack the inversion center, which gives rise in bulk to the called Dresselhaus spin-off coupling. And this is the expressions for bulk. But if we apply to our quantum well, we do a confinement, and we assume that our quant well along the crystallographic 001 direction, and assume that's low temperature, we can simplify our problem. So here we assume that just the lowest subband of the quantum well is occupied with conduction electrons, and moreover we can substitute the momentum by the average value. So along first order in Kz is 0 because of confinement, like translation symmetry, and we end up with a simple expression for the Dress-House term into this specific growth direction. So this expression changes, of course, if you do a rotation in the K and spin, it can have different expressions for different growth of quantum. Here basically there's two terms. One that's linear in K, that's called V1, and the other contribution that's basically cubic in K that I'm going to neglect in this model. So usually it has a lower value than the first one. And the second one, that's the structure inversion symmetry. That's also called Rashford spin-off coupling. That's come because of the also no equivalent interface. So if you break close to the surface, for instance, we can have a step-like composition in the system, and it's also tunable by external electric field. Sorry, perpendicular to the quantum. So this is the expression, and this is actually my model. So this is a very simple to describe a conduction electron in this two-dimensional electron gas spin-off. And the interesting thing here is actually the interplay between these two terms. So alpha is Rashford and beta is Dress-House. So on the right, you can see this dispersion energy. So this, the arrows correspond to the spin direction. But you can see that's isotropic for when we just have one of these terms, alpha and beta. And it becomes interesting when there's two terms, alpha and beta. So in this case, the Fermi contour becomes curved. And this curvature has a very hard impact in the real space properties of the electrons. And one way to see that is calculating the Green's functions and calculating the local density states. I'm just skip a little bit. So what we did, based on that problem, the simple Hamiltonian, was to describe in real space the Green's function. So basically evaluated the resolvent in K space. And for general alpha and beta, we can have a full analytical expression because we are going to still have this angular integral in K space, and the radial integrals we can basically solve in terms of trigonometric integrals. This problem is exactly analytical when just alpha is present in the system. We can write this in terms of Hankel functions. But the interesting thing that I mentioned before about the band structure curvature anisotropy is reflected here in the local density of space in real space. Local density of states in real space. So the first case is just for Rashba case. That's nicely isotropic. And when you have both, you can see the interference between them. So going a little bit further, I'm developed also a very simple magnetic Dopant model, which I solved by the T-matrix formalism, and I do a lot of approximations here. Basically, I'm just assuming that this is a fixed magnetization along the z-axis perpendicular to the quantum well, and I'm assuming that's isotropic scattering, so it's a straight approximation. And neglecting also the spin-off at the site of the impurity, I have this expression for the T-matrix in terms of the scattering phase shift. And this can be actually simplified in a simple analytical model as well, using the Friedel sum rule that's related to the local density of states with the derivative of the scattering phase shift. So if we model our dopant with Lorentzian local density of states with some broadening, so sigma corresponds to each spin channel. And if we have, let's say, a fully magnetized state, you can describe it this model and calculate the NF-dependent phase schedule. So using that, I did, the next step was to find a suitable current operator for the problem. As mentioned last week, there was a remark on Felipe talk about the correction to the correct current due to external fields. And here there's gonna something similar is gonna appear, but we don't have an external magnetic or electric field, but we have effective spin-off field. And this will give rise to a second term that's called the paramagnetic contribution to the current. So this expression satisfies the continuity equation, which is important because this is a ground state property, so it's a steady state. We have charge accumulation, so this is nice. And here you can see the two basic ingredients to have the finite current, which is the spin-off coupling. That's these terms here, the diagonal of these functions. And time reversal breaking, time reversal symmetry breaking. That's given by this T up and T down be different. So these results for the circulation current. It's dissipationless current, by the way. And for the case of just Rashford, it resembles very much similar to the characteristic wavelength is very similar to the Friedel oscillations in charge. And it has a structure that oscillates in different directions. A nice thing that also happens, of course, when we include both terms, so Rashford and Russell together. And you see that's stretching along the symmetry axis, that's 3 pi over 4. As I mentioned before, alpha is dependent on the external field, so it's controllable by electric field. And we can basically tune this alpha to go to be negative with respect to beta, and this will give rise to a density of current along the opposite direction, rotated 90 degrees. But I think the most interesting thing here is that when alpha equals beta, so when alpha equals beta, we call it sweet spot here. For the spin magnetization, we have what's called persistent spin helix. But in the case of the orbital contributions, this is 0. So the current is 0 for alpha equals beta, and is for symmetric values around alpha equals beta, we have an inversion of circulation. As you can see, here is two plots. And I come to the orthomagnetic moment. So here I'm comparing this both, the contribution from these currents and the spin. That's the type of field. As I mentioned before, the spin-off coupling induces inversion of circulation. So here in the orange curve is the spin magnetization close to the impurity, impurity 0. And we tune the alpha by electric field. The optomagnetization basically changes completely around the alpha equals beta. And just to put here, so these optomagnetizations can be probed by fringe fields. So these magnetic fields outside the quantum well. And here I'm assuming that this 2-DAG has now a volume expansion. So I'm assuming that Z is confined, and I use the ground state wave function to calculate this density of magnetic moment and convert the magnetic fields. So on the right, that's the magnetic field probed above the quantum well at a fixed dimension, fixed distance. And on the first column, we see that's the isotropy of the Rashford term, and this also reflects on the anisotropy that I mentioned before, the current and magnetization, local magnetization. So I come to the last part, that's this ability of measuring these things. So as I mentioned, the Zen centers can be used to measure high precision magnetic fields. So basically, you have a Zeeman splitting that can be probed optically. And this states lies on the center of the band gap, or far away from the 5 electron volts gap in the diamond, which it's even coherent room temperature. So it's a very precise, it can have a very good definition in field, and also in dimensions. So here's
Adonai, you have to conclude. But that's perfect.
Just would like to acknowledge the project. That's from the Marie project. Thank you.
Thank you very much, Adonai. So right on time, but not for questions, sadly. So let's start with the next speaker. Online one. Perfect. It's different from the other one.
Hello, everybody. You can hear me, right?
Yes.
And
Recording in progress.
do you see my...
Yes, also.
Okay, you see my mouse. Great. All right. So hello again, everyone. Yeah, this talk will be a bit different. It has a very experimental flavor. I'm going to talk about proximity-induced spin-orbit interaction at the interface of lead molybdenum diselenide. Just before I start, so actually this project is what I basically doing during my postdoc that I started recently at PSI. And just over there, you can find the Swiss light source. It's a synchrotron facility. And somewhere over there, you can find the address beamline or address laboratory that provides the soft X-ray ARPUS. I will first mention what was the motivation to start the study, then I will go to the experimental ideas and what we did exactly, then showing results, discuss them a bit before concluding again. So the material or the study we are doing here is related to spintronic application. Why spintronic? Because right now it is enjoying a very high and fast development in the industry, as well as in fundamental research, especially after the discovery of the magnetoresistance effect that uses the interaction between the electron charge and spin, which is basically the fundamental or basic fundamental phenomenon that spintronic needs as an application. Well, even though with magnetoresistance effect, there was a very high development, I would say, and they reached very nice progress. However, there's a new direction to build spintronic devices, and it's driven by the impact of the strong spin-orbit coupling in the material, which, of course, it's got sort of an image of the interaction between the electron charge and spin. And this is what we'll be interested in. So now we have to pick a system, a material, to study the spin-orbit coupling. There's basically a lot of materials that they provide a spin-orbit coupling, intrinsic one. But there's always a problem with lacking of other properties that we need for the application. Like, for example, a gap or the spin-orbit coupling is not big enough to use it, and so on. So another way to get a new material with the properties that we want depends on the application we are aiming for, is to abandon this very simple systems and going to what we call multifunctional material system. So in this case, we're gonna pick one material that has a property A, let's say, and then we're gonna add it to another component that has a different function at B, and so on, depends on what we are aiming for. And this can be done by taking a substrate and then depositing some other element on the top. We'll have an interface, the hybrid systems, or even doping, alloy, etc. So in this way, we are going to increase the total efficiency of this new system that we are building. Again, depends on the application. So for this, we picked molybdenum diselenide as a substrate. So this will be the hosting system, let's say, the basic one. So it's one of the TMTC material. I guess that most of you are familiar with this structure. So it has the following structure and and this is the corresponding Brillouin zone. Here we have only a 2D Brillouin zone, and this is the 3D Brillouin zone. What's interesting about this material, so one unit cell is composed, we're talking here, of course, about the bulk structure. It's composed of 2 layers, all right? They are the same, but rotated like 30-degree one with respect to the other. And when we repeat again the system, we get the second unit cell. So there's the van der Waals interaction between the layers, a weak interaction, which makes it very easy to, for example, cleave the system and get single layers or mono layers, for example. And this is what many people are doing. So this system, because it contains molybdenum and selenide, the high Z element, so basically it has a spin-orbit coupling, intrinsic one. And then what we're gonna do is we're gonna evaporate on the top of the substrate lead overlayers. Why lead? So lead is a heavy metal. It has a very high Z number, and so then it provides a very strong spin-orbit field, all right? And then the idea was that if we build the heterostructure, we hope that at the interface there will be a transfer of the properties from the lead films to the substrate, mainly the spin-orbit field, and we're gonna increase the spin-orbit interaction and the substrate at the interface. So those are only ideas in theory, all right? And then of course, we're gonna look at the electronic band structure by using soft X-ray opus, all right, at the interface. I have to point here that we are going to, well, we did grew amorphous lead overlayers and not crystalline one. And there's a reason why, even though it's not very common to go for amorphous layers in photoemission. The reason, before I mention the reason why, I have to go through the technique that we're using. So it's angle result photoemission spectroscopy that Christine talked about it last week. we shine the light on the substrate, and then we detect the photoelectrons using the analyzer, and we're gonna get the dispersion with respect to the binding energy and the momentum. Now, why soft X-ray is important here? Because soft X-ray, in terms of photon energies, of course, it's higher than the UV rays. All right. So by increasing the photon energy, so then we are increasing the bulk sensitivity in the material. All right. And this because we are increasing, of course, the probing depth. All right. So here we can not only reach the surface, but also the bulk. And if we have an interface, so we can go through the overlayers to reach the interface where we hope to measure. Okay. Also, soft X-ray is very important because it's better than the UV because we increase, in this case, the resolution in K perpendicular. So then we can map the dispersion in three dimensions, not only in 2 dimensions. And yeah, only one bad thing about soft X-rays that there will be a very important decrease in the cross section. All right, and this will decrease a lot the intensity of the photoelectrons. However, in our case, because we are using a very advanced synchrotron radiation where it's very optimized, the flux as well, so we have a very high photon flux that basically recover the loss in the cross section. All right, and then we have a very high number of photoelectrons afterward. So because of this, we could go to use amorphous overlayers because we know that we will not worry about the non-crystallinity of the overlayers, and we can go through them to reach the interface where we basically are going to modulate the spin-orbit interaction. So this is one thing. And the second thing, it's very important that we use the amorphous LED. So then we don't have a momentum dependency related to LED overlayers, because if it's the case, so then when we do the measurements, we're gonna get a dispersion, an overlap, the dispersion from the substrate, but also from LED overlayers, and then both wave functions and the dispersions will be overlapped, and then we cannot really recognize one to the other, and this is not bad. This is not good. That's why we prefer to use amorphous overlayers, and where there's no K dependency, and we're gonna get like some background that you're gonna see later in the measurements, and it doesn't bother us to only see the dispersion in the substrate. All right, so here I come to the results. Just at the beginning, it's very important, as Jan mentioned during his talk, where we are in the Brillouin zone, all right, whether in the vertical or the horizontal direction. And since here we aim first to look at the spin-orbit splitting, so it is very important to find out where the spin-orbit splitting is in the electronic band structure. So those are basic calculation for molybdenum diselenide without and with spin-orbit coupling. And if we look closely at the K point, all right, with and without spin-orbit coupling, we have a splitting that increases slightly when we add the spin-orbit coupling. But at the H point without spin-orbit coupling, there's no splitting. But then when we add the spin-orbit coupling, we have a splitting of the bands. So from this, we can deduce that at the K point, the splitting is due to the interlayer interaction because we have a KZ dependency in here, and it's periodic. It goes just like that. So then because of the interlayer interaction, the bands will be splitted. However, at the H point, it's only due to a spin orbit coupling. All right, and this will be our target mainly. So this is where we're gonna look. All right. So of course we take the material and we start aligning it to find our alignment. So we start first aligning it along the gamma K direction. So this is the experiment, and it fits very well with the 2D Brillouin zone. And then, because we want to hit the symmetry points K and H, all right, which are presented here, which are in the KZ direction, so then it's equivalent to a photon energy dependency or scan. So then we have to find which photon energy corresponds exactly to the K point and H point. And because actually the C the C vector here is very small. So then the difference in photon energy between K and H is really very, very narrow, all right? So one has to really be careful about how to find the points, right? So that's why we did a KZ scan. I took a cut along the gamma A direction and another cut along the KA direction. And then by following the periodicity, we can find the points that correspond to gamma A or KH and so on. However, I see periodicity and I can say that this is a point, this is another point, and so on, but I don't know which one is what. So here comes, here where we need actually theory. And so Jan with KKR and one-step model of automation, he did the corresponding calculations and he gave me exactly the same dispersion I got, which I don't have it here. I didn't present it because I don't yet have data. But yeah, using theory, you can then find out that this point here is an A, this point is a gamma, and so on. All right. So this is where I could find the photon energies that correspond to each point in KZ direction. So now we aligned.
Fatima,
we know,
sorry,
we
do
know
you
where
hear
our
me?
points are.
Fatima,
Yeah.
you have to conclude right now. Sorry.
Okay, I will go very fast.
Yeah, but very, very fast. So.
Sorry?
Very, very fast.
I cannot hear you.
Do as fast as possible.
Okay, all right. So here's the dispersion for pure molybdenum diselenide. If I take an energy distribution curve at the K and H point, I can measure the spin orbit splitting or the splitting of the bands. So here it's 230 and at the H point is 190 millieV. So already they are different, they are not the same. And then when I add lead on the top, at the K point, the splitting does not change. However, at the H point, it increases from 190 to 250. We repeated the same thing for different thickness of lead over layers. And this is the summary that I got. So we could increase it from 190 millieV at the H point to 275 or 70 millieV. So we could increase it by 80 millieV only by adding 0.5 nanometer of lead on the top. All right?
Fatima,
So
I'm sorry, we have to stop now. Yeah, there is no time left.
Okay, so basically this is it. And then it's only a conclusion of what I said. All right, I'll stop here.
Yeah, thank you very much. Thank you. So no time for questions, of course, and so we will go straight forward to the next speaker. Thank you very much, Fatima.
Mm-hmm.
And for the right, I'll let you.
Am I audible? Hello?
Yeah.
So am I audible?
Yes, you are audible, yeah.
My screen is visible. Okay, so
No,
No sound?
can you hear me?
not.
Can you hear me now?
Oh, yes.
But again, the problem is it is by itself. It's a strange thing.
So, Aditya, I don't think we can hear you. So, there is little problem with the microphone.
Yes, because it's adjusting again the last time. Can you hear me now?
Okay, so go ahead. We'll see how we can manage.
Can you hear me or not?
Yeah, so now yes, but then your microphone is renormalizing it to back. So
Yes. So that's a problem. I wonder what. Should I join again in the Zoom?
okay.
Can you hear me now?
Yeah. Give me a moment, please.
Is it fine?
Yeah, go on. Let us try. What can we do now? What can we do? Because no, the problem is not from our side, so we can't handle anything more. Yeah, just go to try.
Can you hear me now?
I think so, yes.
So can I share my screen and start?
Yeah, let's try like that and we will see.
Am I audible?
Yeah, please go ahead. I mean, I think we have to leave with it. It's a problem with the microphone on your side. So let us go through the slides, and if any particular questions are there, then I think we will address it in a written format.
Okay,
So the discussions also.
So you can hear me?
Yeah, I can, but even the sound
Yeah,
because.
just go ahead.
Yeah, go ahead, please.
So I will talk about the plasmon excitation with the multiple scattering approach in quantum emission energy loss spectroscopy. So already there has been various talks on quantum emission energy loss spectroscopy within and also multiple scattering approach. So we have already heard many lectures. Many experts have already given the lectures. So I will present work, which is I will go by the outline.
plasmon beams is basically part of a set of emission spectroscopy. So, and plasmon is basically response to the system when you have sudden appearance of charge, more hole or traveling electron. So they basically behave like boson and they are collective excitation. So physical theory, which is quasi-boson approximation, was proposed by Henin and then further extended by Buchlau. We are using this approximation theoretical model. So here the first term basically describes the solid with all the electron-electron interaction. The second term with the photoelectron, and the third term gives the interaction between the photoelectron and the solid. So as we know that for sudden approximation, the electron ejected basically neglects the extrinsic interaction with the photoelectron and the other electrons in the system. And here in beyond sudden approximation, we basically include the coupling between the ejected electron and the rest of the system. So this is the scattering theory approach, the Lippmann-Schwinger method, which Anivia already described, and this is the potential beam describing the interaction between the ejected and the ground. So basically what one
I think it's better to stop.
the
The slides will be online.
Yeah, so I will write it. Aditi?
Yes.
Yeah, so there is some problem with the microphone. I think some virus or something. It's completely renormalizing. So you increase it,
Yes.
anyway it brings back to the normal. So which means there is a technical issue in the microphone from your side. So we will anyway we will be collecting the slides of participant talks and we will put it online. So because we cannot absolutely hear you, I can, but nobody else can actually. So we'll put it online and then even send it to all the participants and ask them to write they will go through it and then get back to you actually. Because
Tell her we have to stop.
yeah, so because what we see is only slides moving, so therefore it will be difficult to really.
The slides of bad quality, so it comes from the transmission.
Yeah. So then we will stop. It's really sorry to interrupt you in between because of technical problems, but then I think we will stop it, and then as I told, we will anyway upload the entire thing on the own cloud. So yeah, that would also be good. So or you can record the presentation yourself and then send the entire data to me.
Yeah.
I will put it in the own cloud, so you will have presentation altogether. Then so it can go into that one. Yeah, that's a good idea.
If you can switch to my presentation.
Could you please stop sharing the screen? I have to interrupt you. Yeah, so just a moment.
Yeah.
Recording stopped.
Where is it? Yes, this one. Yeah, this one, yes. If you can control L to put full screen.
And if you can lower down the yes, here. Thanks. Okay, so we are at the end of our school. So first, we want, so Hubert, Jan and myself would like to thank you for your participation and your involvement into the school. Special thanks as well to the participants who became chair during the different sessions. So we hope you have enjoyed the school and found it useful. We are all aware that it was not perfect. It was our first attempt. So we need your feedback. So both for online and remote participants. So just answer, if you can answer questions such as, was it too fast, too dense? We had only 1 day break, so is it sufficient for a 2-week school? Were the question sessions useful? Was there enough time for discussion between the lectures? What about the hands-on? Was it satisfactory? One day per code? Yes, an important question for next time as well. How did you come to know about the school? Through which channel? This is important for us to know. And if you have any suggestion to improve, then of course it's welcome. So you can contact us by mail to give us your feedback. So you can click on the... Yeah. Okay, so where to download the lectures, posters, photos. So you have already some of the links. I just remind them here. So YouTube videos, you can go onto this link. So anyway, it's the YouTube channel of the Lesouche school, and here somewhere here there is some, yeah, I think it is here. It corresponds to our school. So the Zoom videos will be made available on Monday next week. I think that Sunil will send a general mail to tell you where you can download them. So the slides and the posters are on the same location, and you can upload your photos, the photos you took during the school, onto this cloud address. The accounts at the Pilsen Computing Center remain valid until the 1st of October. Please make sure you have paid all you had to pay, okay? Especially the soft drinks here. We remain at your disposal for any further questions, so through mail or if you need through Zoom talks. We would like to thank as well the members of the Best Poster Award for their work. So none of them is here, I think, but Ondra Schip was the head of the president of the jury, Diana Benea, Balázs Usvalusi, John Rare and Sylvain Tricot. We would like to thank also the colleagues who help a lot. So on site it was Sunil for the recording, everything related to the computer here. And Laurent, who took charge of the poster, and if you haven't sent him your poster, and if you wish to do it, please send the PDF file to him. And in Pilsen there was Martin Schafranek, who is here, and who was in charge of the cluster that you use for the hands-on. So after the school, so as I told in the introduction, there will be a book published by Springer Proceedings in Physics. Jan and myself signed a contract with Springer. A tentative timetable is to send to Springer early February, hopefully. So 2 days ago, Jan and myself have been working on the next proposal because we have the deadline on Wednesday next week. So hopefully, if we are successful, it will be held either in October or first 2 weeks of November, and will be centered on spectroscopies, especially multiple scattering and machine learning. And the organizers, apart from Jan and myself, there will be Patrick Rinke from Helsinki, from Aalto University in Finland, who is one of the European experts on machine learning for electronic structure. And finally, thanks to Laurent, we have an idea for an advertising poster for next school. So let us know about your opinion. Okay. Again, thank you very much for your involvement, for being here, and for all the questions that you asked. So, have a safe journey back. Thank you. So, for those of you now who want to have
We'll
lunch,
thank all the online participants who joined us for. Yeah. And also we will thank all the online participants who joined us for question answer sessions and also for all the talks. And despite of the time differences, we had many friends from Japan and other parts of the world. And thank you to all the participants. Okay, so let's applaud them as well. So they made this one work. Okay, so then.